他打我应该可以了，因为打不到人，帮我 pass 打送到对。OK， 可以，没问题。好。Okay, I think we got two master here. I'm not sure Kaishan will be here or not. Let's start. Who should start first? Hey or Jinghun, which one of you want to start first? So basically you will have 10 minutes, right? Okay, and then I will have 5 minutes Q&A. And I think I will set the 8-minute to be reminder. So I'll set 8-minute reminder, and then you will have 2 minutes to finish if you not finish in 10 minutes. Okay. So Seng Junhon send me first. Shall we start with Junhon? So Junhong will tell us about the topology in differential equation. So the theme of the master presentation was we will see topology in the different field. Okay, either it's a mathematic field or applied. Okay. Yeah, so welcome to
the slides not coming.
Yeah. 对吧？现在这样。
Oh, you take a while. Hi everyone, I'm Junhong, and today I'll be presenting about topology and differential equations, where we talk about the existence and uniqueness of the solutions. Okay, so here are the things we're going to talk about, but I'll just briefly go through. So we'll start off with the intro, and then we'll move on to this Bernard's fixed point theorem, which will then be used to prove this Picard-Lindelof theorem, and then we'll show some application. And then later on, we'll be moving to the Arzela-Ascoli theorem, and also how is it applied to prove the Cauchy-Pinot theorem, and then also some applications, and we will conclude this presentation. So to start off, we can see that topology can be used in many fields, and here we'll be using it for the case of the differential equations. So what is the bridge between these two fields? So two main approaches that I found was through contraction mappings and also through compactness arguments. So for the contraction mappings, we'll be using this Bernard fixed point theorem, And then for this compactness argument, we'll be using Zeta squared. So without further ado, let's go to the first theorem. So this is the Banach's fixed point theorem, and it states that let X be a complete matrix space and the function T a contraction. So this right here is the definition of a contraction, and then we will have that T has a unique fixed point X, and then we can find an iteration for xn plus 1, which converges to this fixed point. So to show this theorem, we first define the sequence xn such that xn plus 1 equals to t of xn for the natural numbers n. Then the first step would be to show that the sequence is a Cauchy sequence. So by definition of contraction and the sequence here, we will have this case of inequalities. And then by applying the triangle inequality for n greater equals to n, we will have that the distance between xm and xn will be given by this inequality here. And we see that the term 1 minus k n minus m, as k has to be between 0 and 1, this we can rewrite this as lesser or equal to km over 1 minus k times dx over x1. And then if we choose m to be sufficiently large, we can show that this indeed is a Cauchy sequence. Next up is to verify that the limit of the xn sequences is a fixed point x. So we do this by considering the triangle inequality given here, where we take the distance between x and the mapping of tx, and we see that this shows this inequality here, which would give that this will give the inequality that xm okay, yeah. So yeah, this is just to verify the limit, and then the next one is to show the uniqueness, and then we consider two distinct points, x and x prime, and we can just show this through trivial proof that this is indeed a unique fixed point. And that ends the proof for the Banach fixed point. So how do we apply this into differential equations? We introduce this theorem called the Picard-Lindelof theorem. And this theorem states that for an initial value problem x prime equals to some function of t and x with the initial value xo, if f is continuous in t and f is Lipschitz in x, then there exists a unique solution on this interval here, where beta is the minimum of a, b over m, and 1 over l, where m is the maximum of the f function. So to show this, we want to first show that solving the initial value problem is equal to solving this integral equation here. And then next, we want to define the contraction mapping T over this X subspace here, where it is equipped with the uniform matrix D infinity. And we see that X is a complete metric space. Then we further check that T maps X to X, and then that T satisfy the Lipschitz condition. And then we can then apply Banach's fixed point theorem to show that there exists unique solution for the integral equation. And therefore, this is equivalent to solving the initial value problem as stated in the first part. So one consequence of this Picard-Lindelof theorem is that we have a method to find our solutions, which is through this Picard iteration. So this Picard iteration will be using the integral equation here to find. And we'll look at an example of this. So let's say we want to solve for this x prime equals 1 plus x squared with the initial value of x equals 0. So through a few iterations, we can see that this concludes to the solution tangent t, which satisfies the equation here. However, if sometimes we have really bad integrals, which is in this case, we can see that by the second iteration, we can see that the integral turns really tedious, and yeah, so this is a quite limited strategy to find the solution. So we'll be talking about the next part, which is the Arzela-Ascoli theorem. So previously, using Banach fixed points theorem, we need to have that f is Lipschitz in X. So what if we don't have f is Lipschitz, but we just have f is continuous? So we'll be looking into this in this section. So this statement of the theorem is that a family of function f in the continuous space is relatively compact if and only if it is uniformly bounded and equicontinuous. So the idea of proof here would be through using the eigenization argument. From this, we extract the pointwise convergence on a dense set. Then we apply the equicontinuity to convert that pointwise convergence into a uniform convergence to show that the family of functions is compact. And then to show that compact implies uniformly bounded equicontinuous is trivial, and we can show that easily. So this theorem characterizes the compactness in function spaces, which is another requirement when we don't have the Lipschitz condition. So how can we use this Arzela-Ascoli? We use this to prove this theorem, the Cauchy-Pinot theorem. So this theorem states for the initial value problem x prime equals f, if f is continuous, then there exists a solution on the interval. So to prove this would be to just construct some Euler approximations of the solution here. And then we show that this sequence is uniformly bounded and equicontinuous. Then we can then apply the Arzela-Ascoli to get a uniform convergent subsequence x and k, which converges to the solution x, and we finally verify that x solves the integral equation. So an example of this would be through here, where x prime equals the square root of the norm of x, and we see that the function here is not Lipschitz at 0. So solving implicitly, we will have that x is equal to 0 or x equals to this function t minus c squared over 4 here. So this shows that the solution is not unique, which is in this case when we have no Lipschitz condition. So conclusion here is when to use each theorem. For the Picard-Lindlof, it would be when f is Lipschitz in X, and we will have the result where the solution exists and is unique. And we do this by using the contraction mapping from Banach's fixed point theorem. And for the Cauchy-Pinot, the smoothness of f just needs to be continuous, and we will have the existence of solution, but it's not guaranteed uniqueness. And the method to do this is through compactness argument. Yeah, so that's all from me.
Thank you. Okay, I got a few questions. What in your step 4, right? How do you start your sequence? So that's one thing.
Next one. You mean like
What's your question? You start.
I think this can be like Maybe something like a guess.
Yes,
Yeah.
any point. So that when you start with any point apply P, then you get a steady sequence. That's true. Any point.
No, not. Think needs to be. At least approximate to the after contraction, it be approximate to itself. Approximate to the solution itself. Yeah, like a guess solution. Not sure.
Not sure. Okay. How about slide 6 and slide 6? Verify that the limit of X(n) is correct by infinity. So how does help to verify the limit?
Um,
So you take
Yeah,
X to
yeah.
infinity,
yeah, take
but then how the bottom
so think this inequality goes to 0. Then we have that the distance from tx to x goes to 0 as well.
wait together. Which five got mentioned how to get it?
Uh,
Where do you get the X? What's the existence of
so it just so when using x here, we don't treat it as a fixed point yet, but later when we show that it is lesser equal to 0, then we can propose that it is the fixed point.
where you get X? How do you know the limit?
Because we showed that it is Cauchy, so then we have the limit of the x given by this Cauchy sequence.
If your space is not complete, then the limit might not be this way.
Yeah, so this is only in the complete matrix space X.
Use relatively compact. Can you comment what that?
The compactness here is like, so the functions are bounded in the space so that it doesn't run out to infinity.
I know about the what is relative.
I think it's just compact, but the statement there writes relatively. Yeah, in the paper it's not relative. So article about the proof for the Cauchy-Pinot.
Differently.
Hmm.
I think we just discussed the Topology yesterday. I mean, we just say. Okay, last thing is the Euler approximation. What's Euler?
So this one they just use the. I didn't finish the proof in the paper because it's like 4 or 5 pages. So for this one, the Euler approximations uses something called the Euler polygons. Which,
Piecewise.
yeah, piecewise to approximate the solutions for X.
This seems a more detailed version of the topic itself. Ignore many times jump on again. Okay, Kaijun, can you send me your PD, Beamer first? Later open from here. Next we'll have Pei. 很有氛围感。So we have Pei to tell us about how topology works in the optimization.
Hi everyone. I'm going to introduce my topic, topology meet optimization. This optimization is a very broad area, so I typically choose the non-linear, and in the non-linear, I choose an algorithm method called interior point method. So optimization is a central discipline in applied maths, and it can be applied in economics or the operation research, etc. And it select the best decision according to a specific objective function. And so today I'm going to do some introduction and then explore the conversion of interior point method and establish the topological condition. And lastly, I will explain the barrier function framework and how it applies. So, optimization nonlinear constraint problem. So it will be start with the objective function. In this case, is the minimization problem. As you can see, the problem can be formulated as follows, and we need to make sure that the function is smooth, and G is the inequality constraint, and we have a feasible region called M. So in our case, the solving constraint problem is harder than the unconstrained one because of the boundary structure introduced by the constraint. And classical method like the KKT condition is very good, but is often struggle to near the boundary region algorithmically. So this method, interior point method, reformulate the problem into the unconstrained one by using a function called barrier function. Later, we will introduce the barrier function in detail. And I would like to also mention that the strict interior defined as the strict M, which is the feasible region. For the historical context, interior point method is a modern optimization tool that promote the numerical stability. So as you can see, the feasible region defined as M and the strict M. Strict M is need not to be equal into the interior M. And here's the function that I mentioned, which is the barrier function. The mu is the parameter, and also the convergent behavior. The function keeps the solution away from violating the constraint, and it measures the solution state inside the strict physical region. So as you can see, the limit of the barrier function equal to fx is because of the formula above. It's because when the mu getting near to 0, so it become invisible. That's why the barrier function equal to fx. And when the solution is out of the interior or the street end, it will show the formula as below, approaching to the infinity. In this method, we need to make sure the function is progressive. It means that it guarantees the existence of a minimum over unbounded domain under Mao continuity. So, in order to generate to ensure the existence of global minimum, we need to have some theorem in analysis. The first theorem is the Weierstrass theorem. This is to ensure the existence of a global minimizer for a lower semi-continuous function define a compact set. And the second theorem, this tells us that when a function is guaranteed to have a minimum, even if the domain M is not compact. This is the alternative existence result. So from here, we will start to discuss about the topology on interior point method. So the first one is the isolated subset. It's important to distinguish a particular set of interests, typically a local or global minimizer, from the surrounding space. The next one is the proposition. If a compact subset of minimizer is isolated and all minimizer attain the same function value, then one can construct a compact neighborhood around this subset in which no other point in the physical region achieve the same optimal value. And this the proof. The next theorem is very important. It's about the barrier function, and it's also the core of this presentation. It proves that under Mao assumption, including isolation and coercivity, the sequence of minimizer of the barrier function will converge to the true solution of the original problem. There are some assumptions here. And the first thing we need to do is to show the isolation of the true minimizer. And this proof of the step one is there exists compact set. And the second step, we need to make sure the sequence yk is bounded and has limit point. And its limit point x intersect with n and c, since both n and c are close within a compact set. And the step 4 is provide a proof by contradiction to show that the limit point of the iterate S belong to the set of minimizer n star of the original constraint problem. And the step 5, the function value converge to the optimal value. Yeah. And here's the algorithm. We choose a initial point and then apply the barrier function and adjust the parameter mu until we reach the optimal point. So there are some open questions here. What are the necessary topological conditions for convergence, and how do different barrier terms affect convergence speed? And it's a question also whether the result can generalize to infinite dimensional space. Thank you.
What do you want to
Have you seen like the optimization graph? We choose a function and then like the graph. So there's some optimal point whether we want to minimize or maximize. And then so we restrict certain areas so we can find the optimal point more easily.
but for your M you set gx less than or equal to 0.
Yeah.
So when equal to 0, your long the
Yeah, that's why the barrier function comes in. Barrier function, the function of barrier function is to penalize the function when it goes away from the optimal solution. Like when the function getting near to the boundary and it will penalize the function. Let me show you the formula. Yeah. So, and can you see the line there? Because our function is g less than 0, right? So the inside g must be positive. So eventually the whole formula, like the mu and the ln there, comes 0. So because it means that you reach the optimal solution. You make sure the
mu is 0.
Yeah, the mu we have to adjust also. Like the mu, when the mu become larger. Yeah. Yeah.
The only way to get 0 is your ln.
Yeah.
Is your ln 0.
The g must be positive.
Ln what is it? Ln x equals 0, so x equals to 1.
Sorry.
Ln x equals 0, solve for x. Ln x equals
Yes.
0. Solve for x.
Yeah, x is the solution. I think that there's a method to solve it. Yeah.
This one.
Yes, I'm not familiar with this one, so just now I already watch again. I read again and then I forgot. Yeah. Okay. Go to 0.
You're right.
Yeah.
Yeah. So I mean, like for this thing to get 0, then your GI x should be like around -1, so that you can get log 1. But anyway, can you go to the next page? Next one. Yeah, the point here is like your variable function, right? You call it only defined for GI less than 0, right? Strictly less than 0. Then it seems like you don't need to use M. You use M anyway.
Yeah.
Yeah. Where did you use M?
Your question is used in
Is any theorem proving now? Otherwise, why you introduce it?
Yeah.
Anyway, you use M. But this M is general already. It's not the M you mentioned. Just take your M to be your strict M. Or your M to be compared or something. Not a strict M, right? So can we create what's the statement again? The theorem statement.
which theorem?
M is just random set. Some subset. Yeah, why not just take your M to be a strip of them? What's the point of having that? Yeah.
Yes.
Any idea
Uh,
why we keep M and strip? Straight M is the interior of the front.
Yeah.
So why not just take interior of the Can you go back? Go back a bit on slide 6. Should M did not equal. So should M did not equals to 0.
No.
Why? I'm thinking that I think it's very cool. Standard metric.
is it because the condition not so strict, like the mount assumption?
I don't know. I think to construct some formula. To construct some like any other question?
Inequality constraint. You mean what is the inequality constraint? Because the optimization separate into the non-linear and linear, and then beside that also got separate into unconstrained and constrained.
Is this like the branch multiplier? This
Yeah,
it's
it's related. Yeah.
I think this is a more general. And this is something like subject. So why don't want about why GI less than
Um. Because we set one.
I said why don't
This one I haven't thought.
Said we go back to the barrier. The number is not
become oh no then negative then oh right. But then I also can change the
sign can change to larger than zero, and then the minus sign can go to
okay. If greater equals zero, that's the law. Something example. You can put it to school.
So you are like finding the minimum component, right?
Sorry.
Let's say you
Yeah. Go down. That's one type like you
Which side?
like yeah.
Reading some?
You approach it.
Oh.
It go up to go. But where's your UK? Will you relabel your view here? The view X instead of view.
We do this only when we update the new.
No label. Do you define the K area? What the notation is? You put a function and then view K go to 0. So view K go to 0 to be in another sentence. Suppose mu K is the sequence go to 0.
Mu is like a parameter we
Yeah,
can.
so mu is the-
Yeah.
Mu and mu K.
Yeah.
K is a sequence. The separate sentence then should be separate. Mu K is a sequence. There's no more intense pay. Shall we continue with one more before taking break? Or you want to break first? Let's break now. Okay, so let's have a 中场休息. A long question, yeah, intermission. Okay, let's break until 4:03.啊，是啊。你是说你也是 PhD 4年？啊，因为我的 degree 是4年啊，我的 bachelor。我的 bachelor 是4年，然后我有写论。
这些都是比较，就是你可以不用，你可以用。
对啊。哦。对，它像牛肉面的这种。但每个它会有很多菜可以里面，它可以调菜出来。这是哦，怎么算菜吗？鱼香茄子。半价。肉夹馍，全部半价。吃完60块就30。我要讲其他。
这个，
没事。
我要写这个东西。
然后你可以讲 where the second inequality is even sign。
哦，
你不要就看那，
然后就写这边，然后逗号
where
我然后再
where
逗
the
号。
second is second 的，你要讲哪一个都可以啊，或者 second 的。
可以
呀。
这样子。
Yeah, for the master submission, right? You need to compile the cover page, and then your report, and then I signed you into the Turnitin. So you can do your Turnitin and then reduce the similarity, and then you attach your beamer. I think that's it. Yeah. Okay. So please correct your PDF or your report based on the question just now. Okay.
这样标，这样我标错了。
你看他给你有什么东西？他有时候不会这个字，你给他看他给你什么？
我不知道怎样看的。
按这个，
按这个
那他不会这个字吗？
，OK，麻
你可以加进去啊，你的，加，可以加。
这是一笔吗？我听一下有没有错？
没有吧？
音笔梦，
你念都念，你念。
对啊，是没有错。有些英文字是念的方法
是
跟写的方法有
是，但是有些数学字那个嘞，只要加进去补强。
我昨天把你放的 emoji 加进去。哎，你之前不是有放一个黑月亮的 emoji 吗？我就把它丢进去那个单词里面。要下雨饼。
Continuity compact 在这边嘛，这个 achieve minimum convergence subsequence。
就白色的。
it's a convergence subsequence.
然后还有选择全部跟你学它多点亚系再高一点，再高一点，必须要我今天的没整天这个是空腹，但是那方面的东西要没有你说选票，对呀，什么有什么颜色？marker 那种 tumor marker。呀，啊，对对对对。
Testing. Okay, let's invite Kaishen. So this is a topology in physics.
Very little topology.
A little topology. Okay. So see more on general topology, general relativity.
Okay. Okay, I can start already. Okay, good afternoon, everyone. So my name is Kaishen. I'm here to give my presentation for this class. So it will be sort of a marriage. Okay, per the project description, is a marriage between one field and topology. So this is will be an overlap between general relativity and topology. But spoiler alert, there's not much topology involved other than I will give you an introduction on what general relativity is, what it's really about, and then in this introduction, I'll introduce something called a metric. Okay, but turns out it's not the metric. We will see if the metric that I introduced in the general relativity metric, is it the same as the metric that we learn in topology, the usual definition of the metric. Okay. So yeah, so let's go into the introduction to GR. Okay, so what is general relativity? Okay, so I want you to close your eyes now. If you want to close, you can close. But imagine you're like far out in outer space. Okay, there's nothing there. It's like a vacuum. Imagine maybe you have some planets. Okay, like in a distant point. Okay, far away there are some planets. Now, actually, there is a hidden background. Okay, in this vacuum space, in this outer space, this vacuum space, you can imagine a hidden grid. Okay, a hidden background. Now, Einstein actually found out that this hidden background, this grid, okay, that you imagine, they actually can curve and bend in outer space. Okay, so while you're in outer space, imagine this grid, and this grid actually bends, and this grid actually tells you how you would move in outer space, how particles will move on it, how light will bend. It's all according to this grid. And not only that, not only can this hidden, background grid in outer space, not only does it tell you how these things move, but they actually take the shapes of things that we are very familiar with here on Earth. Okay, so the things that it can curve similarly to like how a sphere curves, how a cylinder curves, and how
many different shapes like toruses, even, okay, curves. And the tools that we use to understand, to study spheres, tori, and cylinders, those tools, we can equally use it to study the reality that we live in, okay, the outer space that you were in just now. Those tools can also be used to study that exact space you live in. Right, so basically what I'm trying to say is differential geometry and differential manifold, all of the techniques we use there, we use it to actually study the physical space that we live in. Okay, so suddenly it's not just about spheres and cylinders you can draw on the whiteboard, but it actually describes a very real part of the world that we live in. But of course, okay, of course in GR, if you have heard of this, instead of considering a 3D space, it is actually a 4-dimensional space. Okay, so there's a bit of a spoiler. Yeah, space-time is 4-dimensional. Now, the 4-dimensional space also has curve-like properties like how spheres would bend and how cylinders would bend. Okay, so actually it is very similar. But now, so let's take a look at how we make this notion, this idea a bit rigorous. Okay, just an introduction to how to make this a bit clearer. So now, an introduction to GR. So I'm going to introduce the notion of metric in GR. So if you remember, right angle triangles, your C squared equals to A squared plus B squared, right? Now, if you want to consider a very, very tiny length, okay, a very, very tiny triangle, you can just call it DC squared equals to DA squared plus DB squared, like infinitesimal length, okay, on this right angle triangle. Okay, let me go and get my marker. So imagine a super small triangle here, right? So this DC square can tell you the length of this triangle, okay? So imagine you have like many different triangles, and suddenly you can go from this point to this point, okay? Like this is the C. Okay, now, so this is, in a way, you can think of this as a distance. Okay, you can think of this as a distance between these 2 points on the triangle. Now, on space-time, okay, on the reality we live in, we can actually have a similar notion as such. But instead of it being C squared equals to A squared plus B squared, we have a negative component in the front here. Okay, so instead of it being BC squared equals to A squared plus B squared, we have a negative component. So instead, it will look like negative dt squared plus dx. Okay, so I'm telling you all this without proof, so as mathematicians, it might feel very weird, but this works in physical reality. Okay, now, so let's continue on and see how this would even relate to a metric that we are familiar with in the usual definition. Okay, so here are slides that. Okay, so let's go here directly. Okay, so earlier, is the space-time interval, right? So this is the analog for the right angle triangle in reality. We call it the space-time interval. In GR, it's normally referred to as the metric. Okay, so let's see a bit of how it can be written as some different notation first before we go and introduce the idea of metric. Okay, the idea of metric in math, right? So this equation can actually be written using tensorial notation. Okay, so this G mu nu here is something we call a metric tensor. So all of this I'm telling you now, but I will introduce it a bit better later. And this metric tensor can be written as this matrix here. Okay, so and then the mu and the nu, the indices here, if you have it diagonally, you will sum up these indices and go from 0 to 1. Okay, 0 to 3. I am going to skip a lot of it, but yeah, so this is how we write a metric in physics. Okay, this is how you write a metric in physics. Okay, so how is the usual metric that we write a metric? So let me write the right. right triangle. Okay, so how is the metric A metric? Okay, so now let's introduce some definitions. Okay, so actually, I know it's a bit messy there, but for now, you just have to remember in the normal space that in the normal geometry that we are familiar with, triangle, triangle, DC squared equals to DA squared plus DB squared. But in the reality that we live in, okay, if you want to consider all of reality that we live in, including time, okay, the crucial part is including time, the right angle triangle part actually becomes, you need to include a negative component. Okay? Okay, so now let's introduce this idea of the metric tensor. Okay, so the metric tensor is actually a function at a point P on the manifold. So a manifold, M is a smooth manifold. Okay, a manifold is a topological space that is locally Euclidean. Okay, so you can just, but it's not important now. And the metric tensor is a function on P, function defined on the point P, that takes the tangent vectors, that takes two tangent vectors and assigns to it a real number. Okay, and the metric tensor has to be bilinear, has to be symmetric and non-degenerate. So bilinear because you're taking two tangent vectors here, okay? So your metric tensor at point P will look like something like this and give you some number C. Okay, and it has to be symmetric and non-degenerate. So non-degenerate means that for all of U non-zero, let's say there will exist a V that is such that GP UV is also non-zero. Okay, so it's just saying that just because one of it is zero doesn't mean the metric tensor will just be zero. Okay, so that's what non-degeneracy means. Right, so now let's go on to the next slide. Okay, so now we have a few parts, right? So we see the definition of metric, positive, definite, symmetric, and has to satisfy triangle inequality. But so far, there is no mention of the triangle inequality in the metric tensor. That's because the metric tensor actually it is not required to satisfy the triangle inequality. Right? Okay, so let me quickly finish. Oh, okay, so that's actually the end. That's actually the end of my slides. But because I haven't finished typing it, but so now let's look at something called the Riemannian metric. Finish it. So in short, the right angle triangle is something that lives on a Riemannian manifold. So this is the usual objects that we are familiar in working with. Okay, the things that we like in math. But in space-time interval, okay, in the reality that we live in, it is actually something we call a pseudo Riemannian manifold. It's pseudo, so this is E. Okay, never mind. So for the Riemannian metric, we would need the metric tensor, okay? But okay, let me write this down. So the Riemannian metric actually satisfies all the conditions of the metric tensor here, with the addition of needing to be positive definite. Okay, it needs to be positive definite, along with all of the conditions of the metric tensor here. So actually, suddenly, now you get something that is bilinear, you get something that is symmetric, and you get positive definiteness. So actually, we are very close to the definition of our usual metric already, right? And also, the Riemannian metric is defined on something called a Riemannian manifold. And on a Riemannian manifold, you will actually induce a topology on it. Okay, you can actually not induce a topology, induce a norm on it. Okay, that is defined in this way. Okay, using the metric tensor. All right, so in that way, the norm, we know the norm will satisfy the triangle inequality, right? So on the Riemannian metric, the triangle inequality is satisfied. Okay. In the end of the day, they are still very different objects. Why? Because this is a bilinear form. Right. Now let's look at the last part, the pseudo Riemann. Okay, there's no more slides. I don't need to go back here already. Let's look at the pseudo Riemannian manifold. So it is actually not that much difference. The biggest difference is that it does not need to be positive definite. Okay, it does not need to be positive definite. So a little foreshadowing earlier, right? There's a negative signature here. So there has to be some consequences to this negative signature on what we would usually hold as sacred as Pythagoras theorem, right? So the consequence is that it does not need to be positive definite. And as such, the norm induced on this manifold, on this system, on this manifold, on the pseudo Riemannian manifold, if it does not need to be positive definite, that means it can be negative. And writing it in physicist notation, this is the induced, this is actually the dot product in the pseudo Riemannian metric. You can have three different signatures. So if it is -1, it is a time-like space. It is a time-like manifold. So time-like means that this manifold that we study moves with time. Okay, so as you experience it now, this manifold will move in time. So you can send a signal from here, from this point on the manifold to this point on the manifold, which is also the next time. Okay, so 0 is null. So null is the trajectory of light. And 1, so when it is positive, it is something we call space-like. So it is just purely the space coordinates, the spatial coordinates of the manifold without the time coordinate. And this just reduces us back to the normal Riemannian geometry that we are familiar with. Okay, so that is the end of my presentation. Sorry for the delay. Thank you very much.
So just now you check triangle inequality using norm. So your norm is defined using metric, or I think your norm. Which one comes first?
Because the norm by default satisfies the triangle inequality.
Define. This
So this defines. Sorry, no. The metric define this one defines.
one define.
Yeah.
Then you should check norm property using.
Yes, but the metric here is the metric here. Okay, then we can check using the three metric definitions here. So if we check, we would find that yeah, so should I check it now? Because it would depend on the exact geometry that we are talking about. Because a Riemannian manifold can be many different things, like a sphere, like a cube, like a cylinder. I think from here, not too sure. I don't think so. I don't know how we would check from here. We're going to check triangle inequality. So this is what we would like to see, right? Yeah, so this exact metric tensor here, it will depend on the geometry that we are talking about. So actually earlier, this space-time interval that I introduced, it is the Cartesian coordinate. So it is the cube, the 3D axis, and the x, y, z. So this is a boring space, right? This is nothing happens, it's just straight all the way. But if we consider, let's say, a spherical manifold, consider sphere, right? Then our metric would look like, okay, so so in that sense, so this is in the GR part, including the GR part. But if this is just, if you look at the spatial part, this would be d omega squared would be dr squared plus sine squared theta d theta squared. So our metric tensor would be from these components here. So our metric tensor would be this. So we can use this to check. Yeah. Using values for the different angles and the different R's. Yeah. Yes, the G is always fixed.
I think there should be a general way.
Because the geometry, it really depends on the geometry you're talking about, right?
I know it depends.
Yep.
Okay, the real calculation depends. I mean, if you fix the G, but if it doesn't work right, we won't call it a metric, because what it meant is like sometimes if you said depend on geometry, that means some geometry don't give you metric, some geometry give you metric. Then I don't think this is what they meant. They should meant that this G with this property here should be a metric.
Yeah, but actually there's also a lot of online sources that just say that the metric tensor, like the Riemann metric, is not to be considered the same as the metric. So actually this is more like an exploration of why so is it actually a metric? So we cannot assume that so it is not necessarily true that the Riemann metric is.
So can you give
I think sorry.
Sure. In that case, can you give an example? Maybe in your report say that this metric tensor doesn't satisfy triangle equality. This one doesn't satisfy positive definitely.
Okay, for pseudo Riemann it doesn't satisfy.
Yeah. But I mean, like, if the way you present it is like maybe for some metric tensor triangle inequality doesn't satisfy, right?
Yeah.
Then there should be some example to that.
Okay.
Otherwise, it should be a proof say that every metric tensor should satisfy.
Okay.
Yeah.
Actually, now that I think about it, the Riemannian geometry, we consider it to be a Euclidean space. This would just be the normal dot product where we just multiply the different 2 points. So Riemannian manifold is always on something that is that makes sense that way. So from there we can sort of see.
Not necessary, because if you are just working in GR, so that's fine. Riemannian manifold could be more general than R.
Okay. Thank you.
All right, thank you. So in that case, before we continue, scan letter is too rush. Can everyone move to this table here? Don't need to bring your stuff. You move to here. Move to this middle part. Move to the middle part. Maybe we invite Ryan again. Ryan, can you help take photo, cameraman? Hey, did I saw cloning just now? Zhen Chen. Did Soning appear just now? He went back, huh? Oh, okay. Yeah, let's take a group photo after seminar or this class photo. 来，
好像拍啊，
就这样拍了。来，move，
不要什么 background。
来。
奇怪，就这个角度。很奇怪耶，这个角度。
太丑。
哦，anytime ready 啊。
1, 2, 3. No counting 啊。
No counting. Just do what you want. 拍到什么就是什么。
看 Candy 呢？Candy。
Vertical one for story.
No one for newspaper one. Okay, thank you. Okay, so this is almost the end of our course. Should we talk about quickly about assignment first? Huh? Revision, not replacement.
Oh yeah.
Yeah. No more replacement. Yeah, revision, we got more assignment and tutorial to discuss. Let's discuss here first. So please take note how I give marks, and then if you see I give you too few marks, and then you can come and ask for me. So let's quickly go through 5, 6, 7, 5, and then 6, and then 7. Okay. Wait, let me. This one. Yeah. Okay. Is it okay? Let's see. Okay, so this one is assignment 7. So let's start with 5. Okay, 5 is a lot of short question here. Ask you to show something is basis or not. Okay, so to show something is basis, there are a few ways to do it. I mean the first way obviously is the definition, right? So you need to use the definition. There are two things to show in basis, right? So you need to be able to cover every point, and then there's another intersection property. Okay, so there's another basis element giving intersection. And then to show two bases the same, how do you show that? Set of basis is just set of open set. Okay, so you have to show that one open set is contained in the other set of open set. And show both sides. And then B, so A is a generate equivalent basis here. So there's a significant thing about this, right? We discussed last time about first countable topology, right? And basis, first countable basis. So you show that A generate the same basis, but what's the significant here? You replace the endpoint by rational number. So you significantly reduce the number of elements inside B. Okay. So that's why we say that R has a first countable basis. Okay, so this is the countable basis B prime. And then B, you show that they don't generate same basis here. No, same topology here. Okay, so why? Because there's one open set that you cannot build from the other open set. Okay, and then for question 2, you you are given the co-countable topology. Okay, so meaning a set is open if the complement is countable, and then ask you whether it's Hausdorff or not. Okay, it is not. Okay, everyone do it well this question. And second is more significance here. So say you have Sn converges to X. Okay, in this co-countable topology, if and only if Xn equals to X for all sufficiently large n. So what does this mean? For all sufficiently large n, this function, this sequence will stay constant. Okay, it's not like the sequence in R, like you can oscillate around the limit point. So in this case here, you really need to be an eventually constant function sequence. Okay. Yeah, I think also everyone did quite well. Part 3 is we ask you to show that this co-countable topology and discrete topology actually has the same convergence sequence, but their topology is different. So meaning open set in one topology is not in the other one. Okay, so let's see here. So we found that actually the 1-point set in discrete topology is not open in TC because the complement of 1-point set is not countable. Okay, so meaning convergence sequence doesn't determine the topology. Okay, from here. Okay, lastly, ask about this identity function is continuous or not between these two topology. The space is the same, okay, but topology is different. So it turns out that F is not continuous, but F inverse is. Okay, I think in our class we also discussed similar thing. Okay, but to check this continuity, you just use open set with inverse image of open set user definition. Okay, lastly, this question, what do you reckon of this question? So, how one? Extra algebra or number theory? Is it number theory? Using LCM, right? Yeah. Obviously got extra algebra, but we are using LCM and then a multiple of integer, right? Okay. Yeah. So it's like kind of making number theory into, look at the topology of number. Okay, topology of number. Yeah. Our space here is just, let me see, n, n, basis or topology of n. Yeah. Can I give this to the short sum number theory? Can. Okay, can. Malaysia crisis. Okay. Okay. So we introduce this basis here. Okay, this basis is a multiple of n. Okay, positive multiple only, because we just care about natural number. And then this topology is called the multiples topology of n. And show that this is the basis, so you show the two things. Okay. So you see, the first thing we show that n can be written as the union of elements in B. So this is equivalent to say that for every element in n, it is covered by one open set. Okay. So this is equivalent to that. Yeah, and then I asked you to write down this 6 distinct neighborhood here. So some of you didn't show that they are distinct, so I took off 1 mark. Okay, so you need to tell me like why they are distinct. Did you have difficulty to find 6 of them? Like, do you stop after you founding M1, M2, M5, M10? You stop. Until ChatGPT tells you you can take union of them. Okay, yeah. So remember from here, what should you remember? Finite union of open set is still open. Okay. Intersection also. Sorry. Yeah, finite intersection, but arbitrary union. Yeah, okay. Okay, in the multiples topology, does every K has the smallest neighborhood? Explain. So a lot of people ask me, what's the smallest neighborhood means here? Actually, I didn't cover this in class, but tutorial got related question, okay, about the smaller neighborhood. So smaller here should mean that these neighborhood, you should imagine they form a chain. Okay, so you should think of this smallest one in that's the neighborhood that living in any neighborhood. Okay, that you could find here. Okay, so here MK is the smallest neighborhood because if U is a neighborhood of K, then there is an N such that K is in Mn, which is in U. Okay, lastly, show that this multiple topology is positive. Okay, I think most of you choose M2, M4, I think. Yeah, but M1 is enough. M1 is big enough so that no one can split from M1. Because, yeah, one is the smallest neighborhood of one. Any question on this assignment? Any question that you're unsure? My markings are on the solution here. You can ask. Try and add on. Anyone? Okay. You happy with your marking or not? No, not happy. You need to come and discuss with me. Okay. Assignment 6. Okay, assignment 6 is about connectedness. Okay, this one I got some comment. First question, I think some of you do it too long, too complicated. Okay, actually it's not. No need so many. Yeah, no need to be too complicated. So the main cases you should discuss is, okay, so what's your space here, X? Either X or Y is irrational. What does it mean? Just one of them is irrational is enough. Okay, obviously both irrational is still in there, but most importantly is one irrational and then the other rational. Show that S is connected. And I think only one, I guess, one or two. Okay, Zhao Shen is one of them. He showed it's directly connected. So using open set. Otherwise, you could use path connected because path connected implies connected, but connected doesn't imply path connected. So what we do here is A1, A2, assume A1 is irrational. Okay, assume the first one is irrational. And then either B1 or B2 is irrational. Doesn't matter. Okay. So the point here is you need to create a path that you are always in this set. Okay, you are always in this set. So if you're gonna make a path up from A1, A2, how do you make sure the path is always in that set? You need to make sure that one of the coordinate is irrational. Okay, but you see, A1 you know is irrational, A2 you don't know. So why not fix A1 first and then use A2 to move to something nearer to where you want to go? Correct or not? Okay, I know some of you use square root 2 and square root 3 as your middle point, which is quite good. I mean, like, right? Okay, 中转账在 square root 2 and square root 3. It's okay, that's fine. But the point here is you need to make sure that your path is always live inside X. Okay, so the point here is if you look at this solution here, we take a path that moves vertically from A1, A2 to A1Y, where Y is irrational. So this is a similar idea here. You move to something both irrational first. Okay, and then you move again. Okay, move one by one. Okay, move one by one here. Okay, so this is the key concept here. And then the other cases should be covered by this kind of argument. Okay, two. All of you use the intermediate value theorem. Okay, so I want to tell you that this is going to come out in the exam again. I teach you to use open set. Okay, so make sure you know how to use this open set argument. Okay. So how to use open set argument here? Some of you try to use, but not very successful. How should you think about this question? Do you have picture in your mind or not? You have picture? What's the picture you should have in your mind? Triangle. Should have the graph of f first, right? Okay, so you got 0 to 1, 0 to 1 here. Then your function maybe live inside here. I don't know how it looks like. But it says that there must be a point P in I such that Fp equals to P. What is Fp equals to P? If you plot this graph out, maybe let's call it Gx equals to X. This means what? It must intersect with this line here. Okay, it must intersect with this line. So how the arguments go? No matter it's open set or not open set, you should assume that it doesn't pass through it. So meaning what? Meaning somehow, don't know, split here. Maybe here, maybe somewhere go here up, maybe go here down, maybe split it. Right. And then what's the argument here? Yeah. So you want to get a contradiction there, right? Either you can show it's not continuous, but in this case, our contradiction will be contradicting continuous image of connected set is connected. So how to contradict that? See, already not reaching the line, right? So what we can consider is this two set here, this two set here. Xy such that x less than y, xy such that y less than x. So what are these two sets? This is exactly the two regions above and below this diagonal line. And then you take this intersect with your curve, it is a open set in the subspace sense. Then what have you produced here? You have produced Fi to be Fi intersect with, let's call the first one G, and then call the second one H. Then this is what? These two are open set, right? In the open in the subspace sense, right? And then their intersection is empty. So this is a this connection of Fi, but F is a continuous image of I is a connected set. But you have a disconnection. Contradiction? Okay, no. So this is the essence of how we type the intermediate value theorem. Okay. But the point here is that, you asked me how to show G and H is open. How to show G and H is open? I think some of you show it. Anyone remember what you did if you have shown this? Two set is open. Inverse of what open set? These are inverse of what? Inverse of what? You want to use a continuous function. Inverse of what? How to show G and H are open? It's not required for this question, but I mean for the completeness of argument, why are they open? Well, the union of them is open because it's a complement of a closed set here, right? If you learn more, this is actually the Zariski closed set, right? But this is a closed set. But now we want to say that the separate of them is open as well. How we see it is open. Yeah, you can do open ball argument. So basically, you pick any points in this region. You should convince yourself that you can draw a open ball. The content is in this region. How then? You should be able to compute the distance to this line here. But what's the problem here? This is just this is what? Projection, right? Your linear algebra. Your linear algebra. What kind of projection is this? Orthogonal projection, right? So you take any point here, you can draw a vector out, right? And then you can orthogonal project to this line here, y to the x line. And then from this length of this orthogonal projection, the other component here, you can build a ball that avoid the line. Does it make sense? Make sense or not? Does it make sense? Make sense? Because this is the shortest distance to your line, right? Okay, so if you avoid this, you should avoid all the other. Okay. Remember, linear algebra, least square problem. Now recall. Shortest distance to the subspace. This subspace is a line. Okay. Right. Okay. Next, I think 3 is quite obvious, right? I think you guys did it well. Yeah. Let's see 3. Oh, 3. Okay. 3. There's one thing is how about if you pick your G not to be X, then you don't need to do anything already. X is just 1. It's the finite subcover you want. Okay. But if it is not X, then it haven't covered yet. But what to do is you look at G naught here. Everything outside is just finite. So you just need to cover these finite points, and then you take G naught to cover everything. Okay. Makes sense? Does it make sense? Complement of G naught is finite because this is the core finite topology. Okay. So you pick one G naught. If it is not X, there's only finite thing outside. Then finite thing just need finite cover because every point should have a open set and cover it, right? If it is a basis. So 1 point pick 1, 1 point pick 1, finally many, and then add the big one G naught and finish. Okay, so extra 1. So there's 1 extra here. So there's a m plus 1 here. Okay. Okay. 4. There's one technical part I asked for you is this one. Okay. You need to argue to me like after you define this G to be intersection, finite intersection, U to be finite union, right? Why the intersection is empty? Okay, this is the part I asked from you, actually. Okay, this is the part I took off the marks. I think most of you know how to apply Hausdorff and then know that you want to take intersection on one side, union on the other side. Again, but it's why the intersection is empty. Okay, this part here. This is very crucial to show that something is Hausdorff. Okay, but in this case here, you are required to show this empty intersection property. Okay. Okay. Last one. Okay, last one. Last one. Some part is tedious and then some part is tricky. Okay, for this question here. Okay, so first part is I gave you isometry and then try and explore property on the isometry here. So first is to prove that isometry has to be injective but not surjective. Okay, everyone did it. Okay. So not surjective, you just give counter examples. Injective, you need to prove it. B is to show that if X is compact, then F is surjective. Okay, meaning Fx equal to X. But then what's the point here? Well, this is like the a bit like the fixed point theorem that Jung Hong did just now, right? So we just consider one point and then iterate it using F acting on it. Okay, and then look at this sequence. Okay, and then study the sequence. Show that there's a subsequence that converges to X. Yeah, and then if it's not onto, then suppose it's not onto, then you should get some contradiction that it's not compact. I think a lot of you, when you show that it's not onto, you build a ball around it. Okay, you build a ball around it, and then that ball will prevent you to have a convergent sequence. Yeah, I think most of you done that. And then this is what happens here as well. C, I think C is fine. So is the conclusion still true if X is not assumed to be compact? So meaning if X is not compact, is it still subjective or not? Okay. Or you just give metric space X that is isomorphic to a proper subspace of itself. So meaning it's not subjective. It's actually not subjective. Okay, lastly here, this proof trying to prove you that compactness imply sequential compact. Anyone when first read this proof, you think it's very makes sense? When you read the proof itself, do you think it makes sense? Do you think it makes sense? 有没有给他骗？ Does it make sense? Seems like quite makes sense that when I first read it. Yeah. It's quite hard to find the flow actually. Okay. Quite hard to find the flow. So the point here is, I don't know if there's another flow or not, but at least this is the flow. So a sequence doesn't converge to any x implies that that exists some neighborhood u at every x such that for any n in n there is small n greater than n such that Sn is not in u. There's no finiteness here. Okay, so but the claim above is finite. Okay. And then the next step in mathematics, you say someone is not true, right? You should give a counter example. But the point here is this counter example is quite hard to give. Why? Okay, a lot of you give a counter example. Just contradict this sentence here. Okay, this finiteness stuff. But you need to remember, we got condition here, you know. We are assuming compactness. So what does it mean? Is it possible that when I add compactness in, this finiteness hold true? Is it possible or not? Maybe possible. You understand or not? So you need to take care of this extra conditional, add in the compactness, right? So you need to get the contradiction such that a space is compact but not sequentially compact. Oh, this example is pretty hard actually. Actually, it's pretty hard. You can find in the book of counter example in Topology. Yeah, that I posted up. There's a reason why I post that book up. You look at it. Yeah. Okay. So actually, this example is pretty hard here. So what we consider here is 0, 1 to infinity. Okay. So I mean product infinitely many times. Okay. By that time, I think we did Tikhonov already. So you can see that Tikhonov theorem tells you that infinite product of compact set is compact. Okay, so this set is compact. But why is it not sequentially compact? This is a little bit of argument here. Okay, there's a little bit of argument here why this set is not compact. And how about Rachel, do you want to explain about this? You want to, yeah, you want to explain about this example? I think you write this example, right? Yeah.
It's just like one, and since like you choose one and each of its like point in the sequence in the coordinate.
So this sequence here is a sequence of sequence, right? Yeah. Okay, so your point inside here is already like infinite. Okay, and then you look at infinite sequence. Choose one coordinate become one. How to choose? Okay, wait. So we are trying to show that sequence. Okay, so we are trying to show that it's not sequentially compared, right? So meaning every sequence there's one sequence that doesn't have a convergent subsequence. So I think you need to pick this sequence nicer. Yeah. So how do you pick this sequence now? So this is the sequence we pick here. consider a sequence of functions such that the n digit here is the binary expansion of x. So what's x? Okay. So okay. So you remember how do we specify sequence here? You know how we specify sequence here? From in an infinite index set. Actually, it's a function. Okay, actually, it's a function from I to I. Okay, actually, it's a function from I to I. But what does this function do? Okay, what does this function do? So this function will read out the n digit once you input an element in I in the binary extension. Okay, the claim here is this sequence here. Okay, this function, the sequence that defined by this function does not have a convergent subsequence. Okay, this is the claim. Okay, so the proof here is by contradiction. Suppose there's subsequence. Okay, suppose there's subsequence. Okay, suppose there's a subsequence that converges to a point A. Okay. Then for each x in I here, what do we do? A n k x converges in I to ax. Okay, so this is what we assume. But then we pick this nice p here. So what does this nice p do? Picking p in I is like I look at one of the index. Maybe the first one, the second one. So this is like the peak one. Okay, I look at the peak one. Then what happened on that line? So this p, we choose this p to have ank p equals 0 or 1 according to k is odd or even. We can do that. Why we can do that? Because this I is big enough. Because this I is big enough. So we can, because you fix ank already, okay, out of this ank, right, I built this naughty p. How I build this naughty p here? This p here has the chance that anp equals 0 if it is odd, and then ank p could be 1 if k is even. Then what's this sequence here? Along the p line, what you get? 0, 1, 0, 1, 0, 1, 0, 1. Cannot converge on that spot. Okay, that p line you cannot converge. Understand? Okay, you should imagine this p is the p column. Yeah. Okay. Make sense? Yeah. Suppose you know that one convergent subsequence, then use this nk here to build the naughty p here. Okay, that contradict your convergence. Okay. So this a bit tricky. Yeah. If you can find an easier one, let me know. Okay, I don't know an easier one. Okay. Any question so far? No question. Okay. If no question, maybe there's some word of encouragement from Jinsen. Maybe you can share with everyone. Now today, Jinsen will write his assignment afterthought. Is it? Or maybe just for algebra geometry. Because it's too hard. Okay. So he said, I do follow Jinsen's advice that he tells me on last Wednesday. He advised me to do it first, although I don't understand very much. In this assignment, there's still too much question I need to verify. He hinted between lines about me overthinking things. Interestingly, every maths teacher I have had said the same. Okay. Though this assignment may be full of mistakes, his advice was actually really helpful given the time constraints. I completed it in 2 days. Okay, here should have an exclamation mark. This also answers a question I have always had: why some people can get things done both quickly and well. Besides having a solid knowledge base and a strong research skills, they don't get handed out on things that might not even matter. And only now do I truly understand what it means to overthink things. Wow. Okay, I think you should write this part out. Maybe you can write a book. In fact, this course has been incredibly meaningful to me, even though doing the doing the the什么？还记得吗？不记得。Doing the assignment 哈，OK， drive me crazy every time。OK， 这边可能也要有一个 exclamation 嘛。It has been constantly sharpening my thinking and constantly testing limits of my sanity. Wow. Good luck to my presentation. Also, this is before presentation and exam. And thank you. I hope I can see you in the next course again. Okay. I think it's very how to say it's very happy okay, as long as out of so many people at least one of you get it I'm happy already. At least one of you could get it, I'm happy already. If you don't get it, it's fine, it's totally fine, because this is a different world, different thinking, right? Okay, you are free to choose your own path. So for the next course, algebraic topology, I won't force you to come on. Okay, if you don't want to come, please don't come. Okay, please don't come. You hard, I also hard, because we are just doing our own job already. If you come to the seminar yesterday, that guy from Imperial College London is not that older than you. He also just do maths for 3 years. Look at what he did and look at what you did. 24岁，他也是3年读大学数学吧？你也是3年吧？对不对？没有啦，就是他读3年，你也3年吧？对不对？
不对
Yeah.
他可能有自学2年啊，是。读完3年，为什么24岁了
？OK，but anyway， 随便，但是就是不会差太多，我的意思是 ，OK，so please，所以我昨天其实跟那个赵胜讲过的，我觉得你们这个班呢，已经算是这个数学系里面是最好的班了，我觉得。OK， 什么叫做最好？就是说你们愿意去学怎么去算什么，但是这个还是 term in the one category called 小镇做题家，听过吗？听过吗？没有听过。It's like you just do exercise, do question, do only， 只是做罢了，做题罢了。我跟赵胜讲什么？我要把你们从小镇做题家拉起来，到可以去讨论数学跟别人。像昨天讲那个才第3年不了，毕业不了，他讲哇 ，my research is this 哦，你呢？你讲得出吗 ？My research is this， 还是 my assignment is this？ 差很多，你知道吗？差很多。OK， 你要想一下为什么我要选这些题目放在里面，你有想过吗 ？I urge you go and think about it. Why I gave you every weekly assignment? Why？ 有想过吗？虐待你，我吃饱太闲空了，我还虐待我自己嘞，我还要跟你改耶。不要这样把自己想的这样重好不好 ？OK 吗？啊？
你的嘴巴在抽筋。
真的，这样讲这种很不负责任的话，什么虐待你，什么这样？
没有，他们说
I don't care， 我不要听。有时候也要像一下丢李冰一样，我要照顾我自己，对不对？不会天天给人家欺负了。你要去吃饭，我要讲完了，你要去就去，拜拜，对不对？是不是？对吧？是不是这样讲？
对。
OK， 你到底有没有想过，我为什么每个星期给了3分？有没有想过？有没有想过？
因为我对啊，
不是 weekly 的 assignment， 是因为就是用那一个星期的东西做就好，你不用东找西找，你明白吗？你明白吗？就是那一个星期用教的东西，你明白吗？你就不用去挖到前几个星期还是什么的，已经选好给你了，就是教完这个做这个，教完这个做这个，教完这个做这个。 你宝宝吗？什么东西？
week 2开始给的，要玩那个问题就是，
我不是week 2给咩？我week 2给啊。
没有有时候来这礼拜要交，拜5交，
对，
在拜4的课才
OK， 好，非常好。你为什么早不要讲出来？怎么不要讲走出来？又不要讲是不是？OK， 我其实有意识到这个的，但是我不是整份东西那个东西在拜4的，我不是，可能只有一题或者一小题在拜4的，我是有意识到这个的。
就是一般哦。
有没？你要讲啊，你没有跟我讲。
但是我们有很大问题吗？没有。
那你又没有问题又提出来，你不是很 contradiction？ 有问题就是提出来嘛，我们就解决问题嘛，不要藏在心里的，这样子不 honest， 很难沟通。你有问题你就跟我讲，我们就实时改进嘛，我们就配搭嘛，搭配嘛，你学我也学嘛，对不对？你不要藏在心里，又不要跟我讲，然后又讲我很坏什么的，是不是？什么传染？对不对？你就讲嘛，你要实时讲的嘛，每个星期问有没有问题，有没有问题？不要，拜6礼拜不可以工作。Supposingly 是不可以。我觉得这个问题都不大，这种都是小事吧。我们想一点大事好不好？那我们小事吧，我们拜5、拜1、拜2、拜3，是不是？呀，什么东西？不知道，还重要啊？又是这个数量重要，还是在问这个问题？我讲这样多，还在问这个问题。请你们长大，谢谢，真的谢谢，请长大。OK， 什么？东西？OK，So anyway， 就是只是说可能我不知道啦吧，就是我期望你有你自己想做的事情，你要做你的，我也想讲我的，我们就这样 OK。但是我还是很感谢你们的，其实就是我觉得这个班是我教过最 smooth 的一个班，你知道什么意思吗？丝滑。OK， 最 smooth 的一个班就是没有什么objection 啊什么啊，虽然你们可能会不开心一点，但是你们基本上是会做的了。但是就是说我希望你们能够更好了。这个不是我以后我也不会再见到你了，有可能你知道吗？我可能跟你活在不一样世界了，但是你从这里学的东西是一辈子跟着你，你明白吗？就是你一辈子跟着你，我们以后可能没有 intersection 了，你知道吗？对吧？是不是这样讲？很有可能的嘛，对不对？但是你学的东西就是跟着你了哦，这就是跟着你走了。好，所以希望大家有一个概念啊，从小镇做题家出来，OK， 不要成为一个小镇做题家。你们已经要上一个 level 了，好，这样才配得起大学这个文凭，对吧？对啊 ，OK，make sense 啊？思维上的改变先，你整个人就会改变了。你思维一直不变，你就不知道在做什么的，其实，你一直在你的框框里面。OK，move up from your comfort zone。OK 啊，我没有对你们有什么恨意啊，我只是说来，我希望你们更好。如果你不要你自己更好，随便你，或者你觉得我讲的不是更好，也随便你，青菜，我没有逼你，OK， 我没有逼你，但是我一定要讲我要讲的东西，对不对？不用，你不用问我，
我也爱你，
可以。好 ，OK，make sense。OK 啊 ，So good luck。OK，good luck your revision。所以你会看到 Gary actually 帮你们 type 完全部的 definition 跟 theorem 啊。对哦，你们没有注意到吗？Yeah，we post post 在那个母的，如果不完整还是什么 ，maybe 你们可以再把它做好一点。那 but anyway I think 他蛮 complete。对啊，他那时候他拿这个 course 也是帮助他理解。Yeah. Okay, so we have 3 more assignments to discuss. Okay, and then revision tutorial version, and then lecture notes, and then maybe we'll give some hints on what is coming up in your exam, so that you can revise, focus, focus your reverse. Yeah. So we're also very thankful to Zhao Seng, because Zhao Seng keep revising our typeset lecture notes. Okay. So, yeah. Thank you. Okay. Okay. Seems like everyone using your stuff, huh? So you have more responsibility or things like. Okay. Just link. Okay. So thank you everyone. Good luck. Okay, in your future. Okay, we're not gonna see again, but we'll see you next week.